Assalamualaikum and hi everyone. We are from Group 7 and today we would like to present our Thermodynamics 1 project entitled Design, Simulation and Scaling of a Rankine Steam Cycle System. My name is Nukirana Suhardi and together with my group members Racha Rian and Dayang Nurul Balkis binti Amiruddin Pramasivam, we will be presenting our study. This project focuses on the design and simulation of a 15 megawatt Rankine steam cycle using Microsoft Excel, followed by an evaluation of its performance and a proposed scale up to 35 megawatts. Without further ado, let's begin with the background of the study. For the background of this study, the demand for electricity continues to increase worldwide due to rapid industrial development and economic growth. To meet this growing demand, power plants must operate efficiently while producing sufficient electrical power. Among the various power generation technologies available, steam power plants remain one of the most widely used systems for large-scale electricity generation. The operation of most conventional steam power plants is based on a Rankine cycle, which converts thermal energy into mechanical energy and subsequently into electrical energy. Therefore, thermodynamic analysis of the Rankine cycle is important because it helps engineers evaluate system performance, identify energy losses, and improve the overall efficiency of power generation systems. Moving on to the problem statement, the increasing demand for electricity requires power plants to generate higher power output while maintaining efficient and reliable operation. However, increasing power generation capacity is not always straightforward. When a system is modified to produce higher output, its thermal efficiency may decrease due to additional energy losses within the cycle. These energy losses can increase operating costs and reduce the overall performance of the power plant. Therefore, it is important to analyze the Rankine cycle and identify suitable operating conditions that can increase power output while maintaining acceptable efficiency. The main objective of this study is to design, stimulate, and evaluate a 15 megawatt Rankine steam cycle using Microsoft Excel. To achieve this objective, several specific objectives have been established. First, a Rankine cycle model is developed in Microsoft Excel based on thermodynamic principles. Next, suitable operating conditions are determined to achieve the targeted 15 megawatt power generation. The thermal efficiency of the cycle is then evaluated to assess system performance. After that, modifications are proposed to increase the power output from 15 megawatts to 35 megawatts. Finally, recommendations are provided for future improvements and enhancements to further optimize the system.
Good morning, my name is Dayang Nurul Balkis and I will be presenting the methodology of our study. First of all, Microsoft Excel is used to perform thermodynamics calculations, mass and energy balance analysis, and the cycle performance evaluation. A simple Rankine cycle consists of a boiler, turbine, condenser, and feed water pump was chosen. The cycle was designed to produce a net power output of 15 megawatts. The model was constructed in Microsoft Excel, including all the calculations, component work duties, heat transfer rates, and overall cycle efficiency. For the system overview, the first component is a boiler. It is the heat addition unit of the system. Water entering will absorb heat and convert it into high pressure, high temperature steam. Second, turbine. Turbine will convert the thermal energy of the steam into mechanical work. Next, condenser will remove heat from the exhaust steam leaving the turbine. Steam condenses into liquid water. Lastly, feed water pump. Feed water pump will increase the pressure of the condensed water before it enters the boiler. There are several assumptions made in this study. First of all, system operates under steady state condition. Changes in kinetic energy and potential energy are neglectable. Turbine efficiency remains constant and pump efficiency also remains constant.
This study utilized Microsoft Excel to develop a Rankine cycle simulation model. steam table data were incorporated to determine the thermodynamics property at each state of the cycle. The calculated state properties were then used to evaluate component performance, including turbine work, pump work, heat transfer, and thermal efficiency. The model was first verified for the required 15 MW power output before being applied to the 35 MW scale-up analysis. After developing the Excel model, the thermodynamics properties at each state were determined. This table presents the thermodynamic properties calculated for each state of the Rankine cycle. State 1 represents the turbine inlet condition and possesses the highest temperature and enthalpy within the cycle. State 2S represents the ideal turbine outlet condition obtained through isentropic expansion, while State 2 represents the actual turbine outlet condition after accounting the turbine inefficiency. The increase in entropy from State 2S to State 2 indicates irreversible losses within the turbine. State 3 corresponds to saturated liquid leaving condenser, while State 4 represents the compressed liquid entering the boiler. Using these state properties, the cycle performance parameter will subsequently evaluated. The performance parameters calculated from the Excel model are summarized in this table. The turbine generated 998.22 kJ per kilogram of useful work, while the boiler supplied 3,103.64 kJ per kilogram of thermal energy. This resulted in a net specific work output of 990.66 kJ per kilogram. Based on the ratio of net work output to boiler heat input, the cycle achieved a thermal efficiency of 31.92%, which is typical for a simple Rankine cycle operating under a specific conditions. The calculated thermodynamic processes can also be visualized using a temperature entropy diagram. The TS diagram provides a graphical representation of the thermodynamic process occurring throughout the Rankine cycle. The process from State 4 to State 1 represents heat addition in the boiler, where the working fluid is heated and superheated before entering the turbine. State 2S represents the ideal turbine outlet condition obtained through isentropic expansion, whereas State 2 represents the actual turbine outlet condition. The increase in entropy from State 2S to State 2 indicates irreversible losses within the turbine. The process from State 2 to State 3 represents heat rejection in the condenser, while the process from State 3 to State 4 corresponds to the pumping process. Following the analysis of the baseline cycle, the model was verified and subsequently scaled to achieve the required 35 MW output. The developed Excel model was verified by successfully achieving the target power output of 15 MW while maintaining the specified operating conditions. To increase the power generation capacity to 35 MW, the steam mass flow rate was increased from 15.14 kg per second to 35.33 kg per second. As a result, the boiler duty increased from 46.99 MW to 109.65 MW. However, the thermal efficiency remained unchanged at 31.92% because the operating pressure, temperature, and component efficiencies were maintained constant. This demonstrates that the increase in power output was achieved by increasing the steam mass flow rate rather than improving thermodynamic efficiency. This successfully met the project objective of scaling the Rankine cycle power plant from 15 MW to 35 MW while maintaining the same thermodynamic operating conditions.
For the conclusion, first, thermodynamics performance of the cycle was evaluated based on operating conditions of 60 bar boiler pressure, 450 degrees Celsius turbine inlet temperature, and 0.1 bar condenser pressure. Then, simulation results showed that the system could achieve the target net power of 15 megawatts with a thermal efficiency of 31.92%. Turbine was the primary contributor to power generation. Lastly, for scaling up, required power output could be achieved by increasing the steam mass flow rate while maintaining the same operating conditions and component efficiencies. For the recommendations of next project, we should include the effects of different boiler pressures, turbine inlet temperatures, and condenser pressures on the overall cycle performance in this project. Then we can compare the ideal Rankine cycle and a cycle with component inefficiencies to better understand the differences between theoretical and actual system performance. Lastly, additional cycle modifications such as reheating and regeneration can be included to evaluate their influence on thermal efficiency and power output.